Okay, so if we have a differential equation, let's say du dt equal to, let's say, I a u, u depends of t, plus a function b that depends of u. Okay, and let's say u naught equals to u0 equals to u naught. Okay, and let's say a is an operator that goes from d to x. Okay, and so the joint b is an operator that goes from a Hilbert space to another Hilbert space. Okay, or at first can be Banach space, but b has to be locally Schlepschitz. Okay, so we will have that the problem has a unique solution u, okay, defined in, let's say, t star t star, okay, and it can happen one of these two things, or t star is plus infinity, okay, or a limit when t goes to t star of the norm of ut is equal to plus infinity. So you can say that, or you have global existence, or the solution blows up at t star. Additionally, you can say that we can reformulate the equation as ut equals to u naught plus 0t I a u as plus b u as ds. Okay, so for example, let's consider what we've already seen a long time, the Schrodinger equation, but let's consider particularly when we have 2 with alpha here, okay, and well, u0 is equal to u naught, but u naught will be in hs of Rn, and we want to consider that s is greater than n over 2, okay, and the reformulation will be ut equal to, well, omega t or wt will be the unitary group of operators we'll be using, u naught plus I 0t wt minus s u s squared us ds. Okay, so we have an adjoint operator here, and we want to know with what we call here b of u as let's say I u squared u is Lipschitz. We want to know if it is Lipschitz in HS or N. So let's consider first BU minus BB. Okay, you can say that this is equal to EU squared U minus UB squared B. and this will be equal to I u square u conjugate minus ib squared b conjugate. Okay, and this will be equal to I u squared u conjugate minus I u squared b conjugate plus I u squared b conjugate. So I add and subtract this, and what is left minus I b squared b conjugate. Okay, this will be equal to I u squared u conjugate minus b conjugate plus I b conjugate u plus b u minus b. So we got this equality. Okay, so we got this. Now what happens if we applied norm, let's say HS? So the norm BU minus BB HS. Well, we can apply the norm here, so we can bound this to a constant multiplied by U squared HS. Okay, and we will have this U minus B HS plus, now we will have this part, and it will be a constant norm B we will bound this part in the following way: 1 plus B always in HS, and then we will have the remain U minus B HS. Okay, so notice that we have this and this, so we are approaching to the Lipschitz bound. So if we ask to the norm of U in HS and the norm of B HS to not blow up, so that is less than equal than R, not asking that much. Then if we ask this, we can finally bound BU minus BB less than equal than a constant that will depend in this bound, and of course ds U minus B HS. So we will be in the conditions of the existence and uniqueness. Okay, so for example, if n is equal to 1, and then we had that s has to be greater than n over 2, so s is greater than 1.5. So for example, for x equal to 1, so for h1 r we will have well, postness and uniqueness. Okay, let's say that exists u in c, well, let's say 0 t star s. Okay, a few not, and well, in this case we can say h1, but it will be all the same for any s that satisfies this. So then you will have that Ts can be plus infinity or the limit of the norm of u goes to infinity, so you have a time where the solution blows up. So if we want to look at global existence and we will consider the case where alpha is equal to 2, we have to consider there are two quantities that conserve. Let's call the first one Qu, that will be equal to, let's say, U normal 2 squared, and the other one, let's call it Hu. Okay, you may say H for Hamiltonian. We'll see that, let's say, the integral of Ux squared minus plus, this will be depending on focusing or defocusing equation, and 1 over 4 u fourth dx. Okay, so let's see the case of q. The one of h I will leave it, but q of u, let's say it is this, but we can also say that it is r integral uxt u conjugate xt dx, and this will be equal to scalar product of u scalar product in L2. Okay, so what will be the derivative of q u t? So this will be equal to the scalar product ut u plus u ut, and by definition of the equation we will have that this is uxx plus iu squared u well plus I u and this again. Okay, and that will be equal to minus I, well, we have to separate all the terms, minus I u squared u plus I u uxx and I u squared u. Okay. Okay, so now let's see that every term that I have here will cancel, because if we look at each individually, we will see, for example, the first term gives us, when we express the integral form, will give us something that we exact the opposite of when we have the expression that is symmetric, let's say, and when we add them we will have 0. Okay, and I'm talking about this and this, and the same will happen with this and this. In this case we will have this with this one. All these integrals are in R, and so we finally will have that dt dq q of ut, it will be equal to 0. Then q is constant, and the same thing can be done for h. H will also be a constant. Okay, that will mean that in a given space we will have that q of u will be equal to q of u naught, and h of u will be equal to h of u naught. That means that is constant, and we will use it later for global existence of solutions.